Okay, in this video, we're going to be talking about drag. And drag is another resistive force like friction, but it's the resistive force that you're experiencing anytime that you're on your little bicycle, right, and you feel all that wind in your face, right? That wind is actually a force that's resisting your motion, right? Or if you skydive and jump from, the airplanes and you're feeling all that, right? That is a resistance as a result of you actually colliding with all the molecules in the air, right? And it doesn't even have to be only air, any kind of fluid. And in physics, fluids are defined both as gases and as liquids, right? So these drag or resistive forces also exist inside of fluids. So, bacteria that are propelling themselves through any kind of a liquid medium are also experiencing the resistive force of drag, right? So now the question is, how do we begin to explore what would even be required to have a drag force or calculate a drag force, okay? Unsurprisingly, so I'm going to just write drag here. And sometimes this is called air resistance or any kind of fluid resistance. Okay. So let's start by a free body diagram of any kind of object, let's say a ball in free fall. Okay. This ball is falling through the air, right? And what force is it feeling? It's feeling its weight, obviously, right? But if this were true, if this was the only force, then every object that fell would just keep accelerating and accelerating and accelerating and accelerating and accelerating and accelerating and accelerating until it was like it had this astronomical velocity, right? But that's not what's happening. That's not what we see, right? Raindrops don't hurt that bad, right? They don't kill us. And you would think that something that was accelerating from as high as the clouds could possibly do that. So what is resisting that? That is drag going in this direction. Okay, now what do you think would contribute to how much drag or how much air resistance this little ball experiences? Okay, well, possibly the bigger it is, right? So I'm going to say the cross-sectional area, right? If this thing is really small, like a little pebble, it's not hitting as much air as it's going down, right? So the area is important, right? Something that is, we see this when we actually see skydivers jump from planes, right? If you jump in this position, right, you're making your cross-sectional area very small, right? Whereas if you're doing a belly flop situation, then there's a lot more resistance, right? Divers also experience this when they assume this position versus doing a belly flop. Why do you think a belly flop hurts so bad? Because you're adding so much more drag to your body, so much more of a resistive force. Okay, and probably the thicker the material, right, the more viscous, right, the more density that it has, that is also going to play a part in whatever this drag force is going to be, right? So, for example, let's say that I'm going through air versus going through water. Obviously, air is going to have less drag than water would, right? So the density of the material that you're moving through is also important, right? What if you're going very slow versus very fast, right? So, for example, let's suppose that this thing is just beginning to accelerate, right? That will probably have less of a resistive force than if it's going really, really, really fast, right? So that implies that velocity also matters, okay? So if you put this together, we can say that there's a drag force that looks something like this, right? This force drag, the resistance that this guy feels, is equal to 1/2 times something called the coefficient of drag, or the drag coefficient, right? This is experimentally determined, and basically, the coefficient of friction, it depends on the relationship between this object and what it's immersed in, okay? So you have C, and then you have rho, the density of the material that you're moving through, right? Like I mentioned, so this is the Greek symbol rho, it means density, times the cross-sectional area times velocity squared. okay? So the best approximation that we have for calculating the drag force on an object is this equation right here, okay? Once again, I'll say it again. This is C, this is the coefficient of drag, and this is something that's experimentally determined, and you would either be solving for it or it's something that would be given to you in a problem, okay? Rho is the density of the material that you're moving through, okay? In this case, air. What is the density of air? A is the cross-sectional area of the thing that's falling, right? Like how wide is it, right? Cross-sectional area of a sphere like this would be a circle, right? So that'd be cross-sectional area in this case would be pi r squared, okay? And then v is the velocity, how fast something's going, okay? So if you guys could go to the next slide, that says terminal velocity. Now there's something that's interesting that happens, right? So you see this picture of this cat here, and I'm going to not use a cat, but I am going to use a little ball again, right? So the second I drop this little ball, or this cat, right? The second I drop it, there's no velocity. Velocity is 0, right? So drag is 0, so I don't experience any drag force at first, right? Okay? But then it starts to accelerate, and now I do have a velocity, so drag force gets a little bit bigger. So I'm going to put a little d, right? Okay? And as this guy accelerates, he is getting faster still, okay? And that means velocity is even bigger, which means that the d now, the drag force, is even bigger, right? Now at some point, that drag force is going to get so big that it equals the weight. You guys see that? There's some key velocity here where the drag force is equal to the weight on the object, okay? And when that happens, these forces are balanced, so there's no more net force, meaning there's no more acceleration, and you can't get any faster, okay? Many of you know this term by the famous name of terminal velocity, right? So terminal velocity is why raindrops don't actually kill us when we're walking in a rainstorm, right? It is because there's some velocity where the drag force gets so big that the forces balance each other out and there can be no more acceleration anymore, okay? So using this, if you guys can see there at the bottom of the slide, it says, use this fact to derive the formula for terminal velocity. So using this fact, how could we actually find out what the terminal velocity of some object might be, okay? Well, let's use our physics, guys. Let's use our Newton's second law analysis, right? If we do summation of forces in the y direction, right, equals MAY, right? Here's what we know, that at terminal velocity, at VT, okay, we know that D minus W must equal 0. True story? Okay. So that means that at terminal velocity, you actually have the situation where D equals the weight. In other words, now if I just substitute the stuff in other words, 1/2 times the coefficient of drag times the density of the medium times A times VT squared equals mg. Okay? mg is just the weight. All right? So now if I just solve this equation for VT, I have an equation for terminal velocity. And what do I get? I'm just going to write it over here, VT equals the square root of 2 times the mass times A over, and by A I mean G, okay, over the coefficient of drag times rho times A. Okay? So, in summary, every object that falls builds up a drag force the higher the velocity is. When that drag force equals the weight, you reach the highest velocity you're going to be able to get, okay? And by setting the drag force equal to the weight, we can solve for VT, and we find out that VT is the square root of 2 times the mass of whatever object that is, right? You're going to have a higher terminal velocity if the object actually weighs more, right? Because it has more inertia, times whatever the gravity is on that planet, and on Earth it's just G, divided by the coefficient of drag, right, which is something you'll be given, times the density of whatever you're moving through, in this case air, right, times the cross-sectional area of the object. All right, so we're going to come back to a later video when we answer the why do we care question as to what is the terminal velocity of a raindrop and how hard are they actually hitting our heads, okay? So we will put this equation into good use when we get there, okay? Until we get there, we're going to attack tension problems, okay? Tension is the last force that we haven't really looked at, and it's the force that involves any time that you have something hanging or suspended from a rope, a chain, or some similar type material, okay? I'll see you there.